Okay, good evening, ladies and gentlemen. What day it is today? Oh, the date for today is July 16, 2026. Actually, this is now already my fifth year uh, doing my things on YouTube channel. For tonight, I will be discussing a long video format topic, and this will be one of the additional subject matters on my long video format, because the topic for tonight will be an addition to my long video format topic, integral calculus. I am done with integral calculus, so if you are watching my channel, you could watch integral calculus from start to finish on my channel. And for tonight, I will be discussing an additional subject matter, which I think is very important in the study of integral calculus. Okay, I adjust my volume. Okay, let's proceed. My topic for tonight will be a subject matter on integral calculus, and this will be the so-called derivation of the area of a rectangle using integral calculus, and I will be presenting two solutions. Okay. Uh, I've been seeing some lectures on YouTube, well, which I think are similar to mine, but it doesn't matter. It's theirs, it's not mine. So again, I will be presenting in how I present the so-called derivation of an area of a rectangle using two solutions. Okay, let's proceed. The subject matter for tonight will be the so-called derivation of rectangle area using integral calculus. One of the important subject matters on mathematics is actually integral calculus, because integral calculus actually it is where the all the formulas on geometry was all or has all emanated from integral calculus, like for example the area of a rectangle. We've been using in geometry the area of a rectangle to be the product of the base times height, or it could be the product of length times width, right? But for those who are not teaching higher mathematics, I don't know if they know that that formula actually emanates from integral calculus. It all emanated from integral calculus. Even the area of a circle, like area of a circle is pi r square, or pi over 4d square, or the area of an ellipse, which is actually equal to pi ab. How come if we try to compute for the area of an ellipse, it's the product of pi times the length of the major axis and the length of the semi-minor axis? And how come that if we compute the area of a what it is triangle, it should be 1/2 the product of the base times the height? And for tonight, I will be presenting that all those formulas actually emanated from integral calculus. And for us not to complicate things, I will be just be showing on how to derive the area of a rectangle using two solutions. Again, using integral calculus. Okay, let's proceed. The area of a rectangle. Okay, hold on. This is a rectangle. We could designate this one as the height, also this one as the base. So in general, if we are solving problems under geometry, to take the area of this rectangle, we'll just take the product of the height times the base, or in some other designations, this could be width or this could be length. It doesn't matter. So in the computation of the area of a rectangle, we just take the product of this height here and this base here, and that represents the total area, okay, covered by the rectangle. So for tonight, I will be presenting a solution which actually the origin of the area of a rectangle. Okay, let's try to present solution number one. Solution number one, because in integral calculus, there is the so-called vertical slice and the so-called horizontal slice. So by presenting solution number one, I will be using vertical slice, meaning vertical slice meaning if we try to draw two lines here, okay, and we try to cross out this one, this is termed to as vertical slice, okay, and to compute for the total area of this rectangle here, we must have to move this slice here from this position here, from this initial position. Okay, we'll move it to the right, going to the right position. Okay, that is by using vertical slice. So actually, if we start from here and it will end up here, at least we know this boundary here and this boundary here. And this boundary is actually termed to as the lower and upper limit. For a vertical slice, the lower limit is this one here, this portion here. And actually, the x here is actually equal to 0. And the final position to cover up the total rectangle, okay, at this location here. X here is actually equal to b. This length here with respect to the origin is actually b. So the initial position to cover up the total rectangle will be at from x equal to 0, x equal to b, okay, by using a vertical slice. We move it from 0, we move it up, going to the right, and stops at the location x is equal to b. So we know this lower limit here, we know this upper limit, and we could compute for the area by using integral calculus. And by using integral calculus, if we try to bring out the vertical slice will be something like this, right? It's vertical, that's why I say the vertical slice. The thickness here will be dx. This small distance here is actually along the x-axis, so it should be dx. And this height here is actually y. You got it? So for this vertical slice, the height is actually y, and the width, the thickness at the bottom is actually dx. So if we try to compute for the area of the vertical slice, again, for a rectangle, it should be the product of y times dx. So the area of this one here will be y times dx. Okay? And the area represented by this one is actually differential area. Okay? So this differential area is the product of y times dx. So actually, I got here a first formula here. Differential area of the rectangle will be the product of y times dx. Luckily for a rectangle, this y here is actually, luckily, it's constant. Okay, it's not variable. Variable meaning from this location here up to here, this y here is not changing. The height is actually uniform. Okay, so for y here, it is constant. So if we now try to compute for the total area of the rectangle, we should move this vertical slice from x equal to 0, x equal to b, and that will now be solved by using integration. This is the symbol for integration. Okay, that's integral. So if we now try to integrate both sides, the integral of differential area will be equal to the integral of y dx. Okay, but the integral of the differential area, that's a basic integral calculus. It will just be simply area. Okay, if this integral sign goes near this differential sign, they will try to cancel out. So the integral of the differential area will just be simply area. Okay, that's integral calculus. That's not magic. The integral of the differential area is just area, and the integral of the right hand side will be the integral, okay, of the product of y dx. Then we shall now try to place the lower and upper limit. And our limits are actually, it should be abscissa. It should be x's. It should be from x equal to 0 to x equal to b. So the lower limit will be 0, and the upper limit will be b, the base of the rectangle. Okay? The integral of y dx. For a rectangle, y is actually equal to h. Why y is equal to h? The equation of this vertical line here, it is actually a straight line, and it is one of the special cases on how to compute for the equation of a straight line. A straight line which is parallel to the y-axis with a certain distance b, or y is equal to, no, that's not y. It should be this one. It should be this one. The equation of this one here is actually y is equal to h. It is constant because at this location here, this is h. At this location, it is h. At this location, it is h. So if we try to compute for the equation of this one by using the equation of a straight line, y is equal to h. And luckily, this is constant. So we could replace this y here by the value y is equal to h. And this is actually constant. Okay? So, bringing back this y equal to h inside, it will become the integral from 0 to b of y, which is actually h. For a rectangle, the equation of this line here is actually y is equal to h. It's a horizontal line. Okay, h dx. Okay? As a rule in integration, any constant inside, we could bring it out, right? So, if we try to simplify this one, it should be h. The integral from 0 to b, the base, the integral of the x. Okay? And the integral of the differential of x, okay, is just simply x. Because if this integral sign goes near this differential sign, they will try to cancel out each other. So the integral of the differential of x will just be simply x. That's why this is x. With the lower limit 0 to b. So this is just a matter of substitution now. This is h. We put the upper limit for x, it will be b. We subtract the value of the lower limit minus, the operation is minus. When x is 0, this should be 0, close quantity. And b minus 0 is just simply b. Right? Right? So in general now, the area of a rectangle is just the product of the base times height. Okay? In general now, for any rectangle, as long as you're having your solution under geometry, if we know this height here and this base here, to take the total area it will just be simply the product of this height here times the base area. You could represent this one as h, and this is base. And other designations, you could represent this one as w, or this should be length. It doesn't matter, as long as it is the product of this height here in this lower area. So in general, from my designation, the area of a rectangle in general, okay, so for as long as we are living in this world, this will not change. The product of the base times height represent the area of a rectangle. That's solution number one. That will be answer number one. That's integral calculus. Okay, solution number two. I will try to move this one a little bit. Solution number two by using horizontal slice. Solution number one is using vertical slice. So solution number two is by using horizontal slice. It will be something like this. It's something like this. This is the rectangle. So solution number two is by using a horizontal slice. The first one is vertical. What's the significance of this one? Either by using vertical or horizontal slice, the derived formula will be the same. Okay, let's try to bring out if they are really the same. So by using the Cartesian coordinate system, this will be the y-axis, the x-axis, this is the rectangle, this is base, this is height, and using horizontal slice, this will be the horizontal slice. So if we try to bring out the horizontal slice, it will be something like this. Okay? This small height here will be dy. It's a distance parallel to the y-axis, so it should be dy. And this height here, or length here, is along the x-axis, so this should be x. And the area represented by this one should be differential area. Okay? So again, if we try to compute for the differential area of the horizontal slice, differential area will be the product of x times dy. So this is x times dy. And to compute for the total area represented by this rectangle here by using horizontal slice, we should move this horizontal slice from this location here, or from this side here up to this. Okay, it is along y. So the initial y will be y equal to 0, right? The equation of this one will be y equal to 0, and the upper limit will be equal to, okay, y equal to h. Okay, it is from 0 to h. This height here is h, and this line here, which coincides with the x-axis, is actually y equal to 0. So the lower limit will be y equal to 0, and the upper limit will be y is equal to h. Okay? I think I made the wrong of this one. The equation of this one will be x is equal to b. Yeah. So to compute for the area now, let's proceed with the integration. This is integral calculus. We try to integrate both sides, right? Like what I said, if this integral sign goes near this differential sign, they will try to cancel out each other. So the integral of the differential area will just be simply area. Okay? And for the right hand side, it will be the integral from, we shall now put the lower and upper limit. The lower limit will be y equal to 0, and the upper limit will be y equal to h. The variables inside will be x dy. But luckily, this x here is actually equal to the base. This x here is not varying. From y equal to 0 to y equal to h, this x here is not varying. In actually, it is equal to the base. That is, x is equal to the base. X here is base, x here is base, x here is base. So luckily, x is equal to base, and it is constant. So instead of placing x inside, we could replace x now by small letter b, the base of the rectangle. So it will become the integral from 0 to h of b dy. The base is constant. As a rule in integral calculus, any constant inside the integral sign, we could bring it out. So this will be base, the integral from 0 to h of dy. And the integral of the differential of y will just be simply y. Okay? Integral sign goes near the differential triangle, they will try to cancel out each other. Okay, so the integral of the differential of y will be just simply y. The integral of the differential of y will be equal to y. This will cancel out, so it will just be simply y. So if we try to integrate the integral of the differential y, it will be y. So base times y, the integral of differential y with the limit from 0 to h. Okay, the limits are actually ordinates or y values. So this is base times the quantity h, the upper limit, minus the operation is subtraction. We subtract the value of y when y is equal to 0. So this is minus y0 plus quantity. So this is h minus 0. It will just be simply h or just simply h. Okay. So the final formula on how to compute for the area of a rectangle by using horizontal slice, it will be the product of the base times side. So this is for a rectangle. So as you can see, by using vertical and horizontal slice, the derived formula are actually the same. Area for a rectangle, vertical slice, the product of base times side. Area of a rectangle by using horizontal slice, it's still the product of base times side. That's integral calculus. Okay? So for those of you who would like to subscribe to my channel is at youtube.com/@proofdavidj.de. If you want to share it, please click share. I uploaded 10 subjects already, and one of the subjects is actually integral calculus. For integral calculus, it should be integration at the start, going to the application problems. So if you would like to watch my integral calculus, it's a complete subject matter. And it's very detailed, no tricks. It's just presented as it is. That is from an experienced professor like me. I've been a professor for quite some time. Okay, and I have taught these subjects actually a long time ago. Good morning from Los Angeles. This is Professor David J. De Los Reyes.